Entanglement is one of those things that, strictly speaking, only exist in quantum mechanics, and is therefore difficult to translate to our classical world and make sense of it, especially in a non-technical setting like popular science. You've probably heard that quip from Albert Einstein about the spukhafte Fernwirkung, the spooky action at a distance, and yes, he was talking about quantum entanglement when he said that. And I've already done a video about entanglement for the Nobel Prize in 2022, but this packed a lot of things into just a 10-minute video. And while I feel it was a reasonably good summary in the context of a Nobel Prize discussion, I always wanted to do more and go more in-depth at a later time. Well, looks like the time is now. So here, I will discuss the very basics of what entanglement is, and almost more importantly, what it isn't, and what you can do with it and what you can't. As this is a video in my series about quantum computation, this is what I will focus on in terms of applications. Entanglement as a resource for quantum computing and quantum information. Also, in the end, I will preview the next videos about this broader topic of entanglement, because there is much more ground to cover. But let's begin at the begin. So, what is entanglement? Just a quick note here, I will not repeat the details of what a qubit is or what a superposition means. If you would like to know more about those basics, please check out my previous video on qubits. And now, back to entanglement. Alright, let's start with some classical examples that are similar to quantum entanglement and that will allow us to visualize some properties of it. The first popular example is Bertlmann's socks. Dr. Bertlmann wears differently colored socks every day, just as a matter of principle. So, if you see Bertlmann turning a corner and you can see a pink sock, you can immediately infer that the other sock that you cannot see is not pink. This example is from John Bell, who also produced the original drawing for a paper. Reinhold Bertlmann is an actual Austrian physicist who worked alongside John Bell at CERN and who actually only ever wears differently colored socks. He also published an excellent textbook about quantum physics and entanglement just recently. However, a more useful example is a pair of balls, like pool balls, because we can separate them over a great distance. Let's assume you have one ball with 0 written on it and another with 1. And you randomly pack them in boxes and send them to Alice and Bob, who are very far apart. As soon as Alice opens her box and sees a 0, she immediately knows that Bob has the ball with the 1. This is an example of correlation. The two numbers are not independent, but connected. If one ball is 0, then the other must be 1, and vice versa. We say they are correlated. And note that there is nothing mysterious here at all. The simple fact that if one ball shows a 0, then the other one must show the 1 is completely self-evident, and there is no spooky correlation at all at work. Of course it's 1. It always has been. That's what we prepared. Also note that there is no need for a signal going from Alice's ball to Bob's ball telling it needs to be 1. Because again, it always has been. Furthermore, the separation between Alice and Bob is insignificant. Whether they open their boxes in the same room or on different planets, it makes no difference at all. One ball will always have a 0 and the other must always have a 1. We can go a step further and give the balls a second number. Let's say the number we've been talking about so far was just a number at the top of the ball. But if you turn the ball around, there's another number on the bottom of it. These have been prepared in the same way as the top number. The only difference is where on the ball they are written. Also, top and bottom numbers are completely independent of each other. Alice and Bob can now not only measure the top number of the ball, but instead turn the ball around and measure the bottom number. In this case, they will observe the same correlation as with the top numbers. When Alice finds a 1 at the bottom, she instantly knows that Bob's ball has the 0 at the bottom. etc., etc. And no matter how often we repeat this experiment, we will always find the perfect correlation between the number on Alice's ball and Bob's ball, but no correlation at all between the top and bottom numbers for each person. These will be completely random. And this is as far as any classical analogy can take us. And so far everything was pretty normal and obvious. And it's time to change that. So let's go to proper quantum entanglement. So, the moment Alice opens her box, she sees the number on the ball. For example, 0. Okay, but has that always been 0, even before somebody could look at it? So do things just have properties and looking at them just reveals them? Or does the measurement itself determine them, create them even? Well, our usual classical idea of reality is the former. The ball shows 0 because it always has been. We just didn't know, but that doesn't change the reality of it, obviously. Quantum mechanics, however, supposes the latter. The number 0 in a quantum system is created by the measurement. And talking about the property before measurement doesn't even make sense. And here we are already looking down the rabbit hole that is Einstein's EPR paradox. So, how real properties really are. And all of this will be discussed in a dedicated video. But now, let's look at the quantum equivalent of our numbered ball example. The balls are replaced by quantum systems, in our case qubits, and they are prepared in the entangled state psi+. Here, the first entry, colored red, always describes the first qubit held by Alice, while Bob's qubit is colored blue. Just as with a single qubit, this is a superposition, just of 2 possible outcomes for both qubits. This state describes a 2-qubit system that is correlated and non-separable. This is what we call an entangled state. And we already talked about what correlated means. That the measurement results for both qubits are connected. If I measure one qubit and get a 0, then the other qubit must give a 1 result. So the results are still random. I cannot predict whether I'll get a 0 or 1 when measuring the first qubit, but whatever result I do get for this one, I know that the second qubit will get the exact opposite result. Note, we've been using this particular state so far, also in the classical case, but this is just an example. The 2 qubits could also be in a different entangled state, where they're always equal, as in the phi+ state. The important point is that their measurements are always connected. This is the correlation we are always talking about. This is strongly linked to the second property, that such a state is non-separable. This means that an entangled state cannot be separated into 2 single qubit states, like this non-entangled state can. So an entangled state exists only as an explicitly 2-qubit state. Because the point isn't whether the first qubit is 0 or 1. The point is always the correlation of the 2 qubits together. The correlation is the entire thing. And it is interesting that the description of the full system can only be given in terms of the full system, not in terms of its components. And this means that in a very real sense, even though the complete system has 2 parts, it is only one thing. Another interesting aspect is that entanglement is both local and non-local. It can only be created locally, so you need to be in possession of both qubits and operate on them locally to entangle them. And that's why we say entangled qubits always must come from the same source. Once the entanglement is established, however, location does not enter into it anymore. You can take the 2 qubits to literally opposite ends of the universe, and if they were sufficiently isolated, they will still be entangled. And having this top number and bottom number is also represented in quantum mechanics. And actually, that was the entire reason why I would introduce it into the classical example in the first place. In fact, it is more interesting than that. I can rotate the measurement basis, meaning I can just measure the qubit in a different direction, and I will always get a 0 or 1 result, and this will always be perfectly correlated to the second qubit. Quantum systems that are entangled in one basis are entangled in every basis. This raises a very interesting question. What do I get when I start making measurements in different bases? For example, Alice will measure her qubit in one direction, while Bob will measure in a different one. Well, turns out this also leads to some correlations, and this directly leads to Bell's inequalities and Bell's theorem, which is an incredible possibility to actually measure whether reality is really real. But again, dedicated future video. In summary, the big differences between the classical numbered balls and entangled qubits is that the quantum system is in a superposition until it is measured. It is neither 0 nor 1 until then. Or both, if you prefer. Also, when entangled in one basis, qubits are entangled in all bases. This relatively simple change creates a lot of explanatory problems though. Before, it was clear why Alice's ball was 0. It has always been 0. But if Alice's qubit can either be 0 or 1, and instantly after Alice's measurement, Bob's qubit will always be the exact opposite. This immediately raises the question how Bob's qubit knows what Alice measured, especially if they are far apart. In our classical way of thinking, this would imply some sort of signal, and it would have to be instantaneous. The best analogy I could give you is that quantum systems have absolutely no property whatsoever until they are measured. And as soon as they are measured, it's as if the system had always been that way. And yes, I realize that's a contradiction, but it's the best contradiction I can offer here. When people hear that a measurement result in one place has an immediate effect on another place, irrespective of distance, they immediately jump to, oh, so we can communicate faster than light now. And to be fair, that's an easy mistake to make. But no, you can't. Okay, but why not though? Why can't we just distribute thousands of entangled pairs between Alice and Bob? And Alice uses those to signal a message using her qubits. Well, because you cannot signal by measuring qubits. Remember, any measurement result Alice gets is completely random. Yes, if she gets a 0, Bob immediately gets a 1, but it's not up to her to get a 0 or a 1. She has no choice. All she gets are random numbers, and that same sequence of random numbers is also repeated at Bob's, just with zeros and ones replaced. And we have a name for a signal like that. It's called white noise. It carries no information. Okay, it doesn't work as simple as that, but can't we be more clever about it? In 1982, physicist Nick Herbert came up with a clever proposal. When Alice wants to send a 0 signal, she measures her qubit in C basis, and to send a 1 signal, she measures her qubit in the X basis. This won't immediately help Bob, as all he'll get is a seemingly random result, but if he just copies the state of his qubit after Alice's measurement, and generates thousands of copies of it, he can measure all of them, and from the distribution of results, he can infer what his state was, and consequently, what Alice's base was, and consequently, what Alice was trying to send. And this idea upset or thrilled physicists for a bit, But in the very same year of 1982, the no-cloning theorem was proven. It showed that an unknown general quantum state cannot be copied. So while Herbert's idea would work if you really had thousands of copies of a state, there is no possibility to get those copies in the first place. And it turns out that there is no way at all to use entanglement for communication faster than light. And to today's best knowledge, it is absolutely impossible. Another important limitation is that entanglement is basically just a special form of superposition. And superposition does not survive measurement. So once an entangled pair of qubits is measured, the entanglement is gone and cannot be reinstated. You'd just have to move both qubits back together again and re-entangle them the exact same way you did originally. This also means that entangled qubits are vulnerable to noise and decoherence, which will degrade or even completely destroy entanglement in the same way a measurement does. So entanglement is very much a one-use resource, and also you have to protect it from the environment and isolate it for it to remain useful. Entanglement is often called a resource for quantum computing or quantum information because it allows us to do completely new things. Foremost of those is probably quantum teleportation, which allows us to teleport a quantum state, so pure information, not matter, from one entangled qubit to the other. Again, instantaneously and regardless of distance. Okay, the word instantaneously needs an asterisk here though, because the teleportation protocol requires a regular communication line in the end. Otherwise, we're just teleporting white noise again. Remember, no faster than light communication. There are also some small applications like superdense coding, which is probably the most straightforward use of entanglement. A single pair of entangled qubits contains 2 bits of information, so you can communicate those 2 bits of information despite each party only accessing a single qubit. Interestingly, it was found that entanglement can also be used as an alternative to quantum error correction in many cases. Instead of correcting the errors introduced to a state in a noisy channel, the channel is used to transmit entangled pairs, and those then can be used to teleport the desired state. This can even work for channels that are too noisy for regular error correction. There are also some encryption schemes between 2 parties that are based on entanglement. The basic idea is that Alice and Bob share a number of entangled qubits, which can be used to transmit information between them. Whenever a third party interferes with the entangled qubits, invariably the entangled states are changed, and this change can be detected with exponential likelihood. So entanglement was found to be a property of quantum states, just like energy or entropy. The quality of entanglement can be defined and measured as fidelity, and it's possible to process a large number of entangled states of low fidelity to get one entangled state of high fidelity, which is called entanglement distillation or purification. And the opposite is also possible. You can spread around high fidelity entanglement to get a large number of low fidelity entangled states. Entanglement dilution. Finally, we have only been talking about entangled pairs in this video, but there is also multi-particle entanglement between 3, 4, 5 or even more qubits. These complex entangled states may allow for completely new algorithms or even architectures of computation, but they are increasingly difficult to create and sustain. Alright, this was the video about the basics of entanglement. But I'm planning on or already working on a number of additional videos about this general topic. The first will be a discussion of Albert Einstein's EPR paradox. because that is pretty much what put entanglement on the map in the first place. And it posits some really deep and interesting questions. While it eventually failed in its original goal, it is still a vitally important part of the entire discussion. Immediately following that, John Bell's theorem built on the questions brought up by Einstein and, contrary to everyone's expectations, showed a way to open Einstein's assumptions to actual experimental tests. Anton Zeilinger was awarded the Nobel Prize in 2022 for entanglement-based experiments. And I'm planning several videos about his most interesting work. At a minimum, this will include entanglement between three particles, the GHZ state, quantum teleportation by entanglement, and experiments with entangled pairs in space. Expect the first two pretty soon, and all the Zeilinger stuff a bit further down the line. Make sure to check these out if you enjoyed this video, and also subscribe so you don't miss out on stuff like this. See you next time.